Okay, so we will start. Okay, so we'll start. So last time what we see is we talk about a set of linear multi-step methods so far, and then we talk about the convergence of those methods, order, consistency, and then stability, absolute stability, and then a combination of two linear multi-step methods as predictor corrector methods, and then we see the absolute stability of those methods as well. Right? So today what we are going to do is we are going to start a new concept called Runge-Kutta methods. Right? Runge-Kutta methods. So here in Runge-Kutta method, what we are going to do is we are going to see, actually we are going to start with the Euler method, right, which you studied in the first chapter. It is the Euler method. And then we see that the Euler method is basically a Taylor's approximation for the solution y at Tn plus 1, right, when we approximate the Taylor's expansion with first derivative, right? So that is how, if you notice that, this is how okay, so this is the Taylor's expansion at first order, right, approximated at the first derivative, right, with the first derivative. So from this, we get the Euler method, right? So that gives you y of n plus 1 is basically equal to yn plus 8 times f of tn comma yn, right? So from this, we can see the Euler method, right? So approximation of Taylor's expansion of y at Tn plus 1 with the first derivative leads to the the Euler's approximation. So obviously you can think that if we can expand this a little more, right? So h squared over 2 y2 prime Tn, then that would be a better approximation, right? So if you have one more term, then that would be much better approximation, right? So because all these are approximations, so as long as you increase the number of terms on the right hand side, you get better and better approximation. But unfortunately, increasing that leads to another problem where you need to know the derivative of the function, right? Higher order derivative of the solution or at Tn, right? So even if you go one more term, then you need to have second derivative of the solution. If you have one more term after that, then you need to have third derivative of the function. So in that way, you know that expanding this will lead to another problem, even though the approximation is better, but that leads to an issue where you need to know the derivative or higher order derivative of the solution. So how we can approximate or how we can fix this problem is how we do the Runge-Kutta method, or what we do in Runge-Kutta method is basically we try to fix this issue, right, by using this kind of a function, right? Because this is a function which is known to us, right? By using this function, we try to fix this issue in higher order Taylor's expansion or Taylor method, right? And then that leads to the Runge-Kutta method. So in order to derive the Rangota method, what we are going to do is to, after writing the introduction, we are going to talk about Taylor's expansion or Taylor's methods, higher order Taylor methods, and then by using that, we try to see the development of Rangota methods. I should use capital. Okay, so this is the problem now, right? So we want to improve the rate of convergence of Euler method. So basically you want to look for the better approximations than this linear approximation of Taylor's expansion, right? But going for higher order approximation leads to higher order derivatives, right? So how we can fix that issue is that idea leads to the Ranguta method. So what they do in Ranguta method is actually they use a combinations of compositions of the right hand side function f, right, to approximate the derivative. So in order to do the Ranguta method, so obviously you know it is a expansion of Taylor's method. Right? So we will try to start with the Taylor's method, right? Basically we will try to do an example, right? And then we will try to see how we can expand that into the Ranguta method. Right? So that is what we are going to do here. Right? So first we will start with the Taylor's method. And so we will try to develop a Taylor method for the given initial value problem, right? Consider okay, so let us consider an initial value problem which look like this. Y prime is equal to negative y plus 2 cosine t with the initial value y at 0 is equal to 1, right? So we can see that we can easily see that the real solution is sine t cosine t, right? So that is the real solution. So that's not a big thing here. By using the knowledge you have in the first year, you can always find the solution, right? So that's sine t cosine t is a solution. So what we do is now we will try to approximate the Taylor's expansion, right? So approximate y tn plus 1 by using Taylor's expansion. Right, so when you approximate with the second derivative, right, sorry, you have 2 tn. Right, so this is basically an approximation. Right, so let us approximate y tn plus 1 with the second order Taylor's expansion with second derivative. Right. So in this case, you know that so h cubed over 6, 3 factorial 6 y 3 prime psi n, right, with this psi n between tn and tn plus 1. That's obvious for you. Okay, so this is how you approximate by using Taylor's expansion. So when you approximate, you know that you have to get rid of the rest of the term. So that becomes the truncation error. So you keep it with the leading term or dominant term, that is h cubed over 3 factorial, which is 6 times y3 prime. Right. Now, so we will try to evaluate these two. Right. So if you want to approximate y at Tn plus 1, then you have to evaluate the right hand side of this equation. Right. So if you want to evaluate the right hand side of this equation, then obviously you know you have to find y prime and y2 prime. So you already know y, so that is how you are going to do it. Right. So y2 prime, you differentiate. Right. So y prime is there, so you can differentiate that. So that is negative y prime of t plus 2, and when you differentiate cosine, you get minus sign. So let me change this to minus. Okay, so by 2 prime you differentiate and you get this. But you have a formula for y prime. It's y prime is minus yt. So minus of minus yt plus 2 cosine t minus 2 sine t. Right, so minus into minus plus yt minus of 2 cosine t sine t. So that's clear for you now. Okay, so you evaluate y2 prime and you already know y prime. Right? Okay, so you can substitute here. Approximately equal to y at Tn plus 8 times y prime is negative y at t plus 2 cosine t plus h squared over 2. So let me write it here. Y2 prime, so y at t, actually Tn, no? Okay, so what you do here is you basically substitute in this equation. Right, so ytn plus 1 is approximately equal to ytn plus h time y prime tn. So y prime is here minus yt plus 2 cosine t, but t is equal to tn here, right? And then you have y2 prime computed, so you can do that. So from this you can write the numerical method, right? So now you can see that you derive the Taylor's method here by using the true solution. Right? So if you know the true solution, then you can derive the formula, right? Not necessarily true solution, but you can always derive the formula by using this, right? So that is how you get the Taylor's expansion, right? No, Taylor's method. Okay, so now this is how you derive the Taylor's method, right? So with higher order functions, right, you use the right hand side function, right, to get a numerical method. So here you can notice that the truncation error for this term has h to the power 3, right? But in Euler method, right, the truncation error will have h to the power 2. So you can expect that this method will converge faster than the real Euler method, right? So let me write down that as a remark here. Okay, so this example tells you that, right? So now, as an example, you can see the approximations, right? So in by using Taylor method and this method, right? So then you can see that which one is better, right? So which has better convergence than the other one, right? So that's just a numerical computation exercise. So you can try your own the rest of the things, right? So now what we have to do is to now this is a second order formula, right? So now we will see what happens if you go for higher power of Taylor's expansion, right? For a general uh, first order differential equation, right? Right, so we will try to consider the Taylor's method for a general initial value problem, right, which is the standard initial value problem we use. Okay, so this is the initial value problem we use, right? Y prime f of right. So this is the general initial value problem we consider. Right. So now let us take a Taylor's approximation up to pth derivative. Right. Right. So this is an approximation. Right. So let us consider the teeth power approximation up to pth derivative. Right. So in this case, you can see that the truncation error is this. Right. So by using the standard notations, we see that we have the truncation error like this. Okay, so this is simple because you just take the Taylor's expansion and then you just take the Taylor's expansion approximated with p derivative. So obviously the next derivative gives you the truncation error. Now comes the interesting part. Now if you look back at the example, right, to approximate y prime, you have the formula given in the problem, so that's fine, right? Y prime is f of t comma yt. But when you take the derivative of y 2 prime, you know that you take the derivative of this, right? So just for your just to see, right? So okay, so this is your y2 prime. Right? So now you can see that this is a two variable function, right? And more importantly, this y is also a function of t. So you can see that you actually have to go for the total derivative here, right? So actually what you have to do is to, right? So you have to take the derivative of the function, right? So when you take the derivative, you can see that this is actually sorry. Right, so this actually takes this form, right? Derivative of the function respect to y and then times y prime, right? So actually, you know this, right? So I'm skipping a few steps, but you know that, right? So it's capital Y, I could say. Right, so this again, I can, oh yeah, it's fine. Right, so you know that the total derivative formula, right? Derivative of the function respect to t plus derivative of the function respect to y times derivative of the y respect to t, right? But this is y prime, right? So you know that this is actually y prime, but y prime is actually f. So that is why I use the notation f sub t, right? The partial derivative of the function with respect to t plus f sub y, partial derivative of the function with respect to y times derivative of y respect to t, but that is equal to f again, right? So you know that it is with respect to f again. So you have a, so this is how we can define a new notation here, right? So ft is df over dt, fy is dy over dt. So now, if you want to get y3 prime, you can see that you have to differentiate this one more time, right? So that is a good exercise for you to see again and again by differentiating this. Okay, so I'm straight away going to write here. Right, so if you differentiate one more time, right, you can see that you have to differentiate this respect to t, So again, chain rule, right? T respect to t plus t respect f respect to y times y prime, so that is f, right? And then when you differentiate this, you keep this and differentiate this, so y respect to y times y prime times f, so f squared, and y respect to t times this, so yt this, and then keep this and differentiate this, right? Product rule, so this then this, right? So but you obviously know ty and yt are same, so you can summarize this as this, right? So okay, so like that you can write down the derivative, right? So higher order derivatives. Okay, so now what you can do is you can substitute these patterns and get to a Taylor's formula, right? Okay, so you can write the Taylor's expansion like this, right? So here, obviously, you can see that the y prime is a function of f, right? And then this y2 prime is a function of f, and basically it is a combination of composition of functions, right? So it is a composite function, right? Fy circle f, right? And then combination of derivatives, and it is a function, right? But you can see that obviously there is no derivatives here, right? So these function has no derivatives, but all of them are written in terms of the right hand side function f and its derivatives, right? So you can always find the derivative of the right hand side function because that right hand side function is always known, right? So this is how you do the Taylor's method, right? And clearly the convergence is clear, right?